joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Okay, so hello everyone. Thank you for joining us today and welcome to today's webinars from our Standard Activity Board series and today's presentation from the Standard Activity Board's Standard Committee. My name is Emeriau and I am the Vice Chair of the IEEE Computer Society Standard Activity Boards. Before we get started, I would like to adjust some housekeeping items. This webinar is being recorded. You can ask many questions in the Q&A box you see on your screen. The speakers will answer as many questions as possible. When submitting a question, please reference the slide. The goal will be to announce a quick question or two after each presenter, and we will bring all of the three speakers back online for panel discussion and a formal Q&A at the end. A copy of the slides and the recorded webinars will be emailed to you tentatively tomorrow. The field of quantum computing is expected to experience significant growth and expansion over the next decade, driven by investment over billions of dollars. Get ahead and learn about the future of the IEEE Quantum Week about the quantum computing. As part of this event, you will have access to a career fair, 9 keynote speakers, 32 workshops, and over 150 technical papers, all related to the quantum computing. More information about the Quantum Week taking place in mid-September this year, just outside Seattle, will be shared after the webinar. Plus, you can always learn more about the event at our official website, computer.org. Circling back to today's presentation with our three speakers, we are very happy that one of the co-founders of the Quantum Energy Initiative and two of the industry vendor partners will showcase here in this webinar their early work on how to evaluate and optimize the energetic footprint of quantum computing, which is really a popular and timely topic nowadays. A disclaimer from the IEEE SA Standard Association Standard Board by law for this webinar. These are the personal views of the speakers rather than the formal position of the IEEE throughout this presentation. And now, let me introduce our first speaker, Dr. Alexia Auffèves. Alexia is a research director at CNRS and an expert in quantum energetics. She runs the CNRS International Research Lab in Singapore and co-leads the quantum energy team in France. After an experimental PhD under the supervision of Nobel Prize winner Professor Sir Arrows, she takes a position at CNRS in 2005, where she works on theoretical quantum optics for quantum foundations and quantum technologies in strong interaction with experimenters. She promotes the physics philosophy interface and develops a new interpretation of new physics, the quantum physics, with her collaborators. She has coordinated the construction of the Grenoble Quantum Hub, which she had from 2017 to 2022. In 2022, she launched the Quantum Energy Initiative, in short form the QEI, an interdisciplinary and international research night to understand the energetic footprint of quantum technologies, along with a few collaborators. And similarly, 2023, she is the chair of the IEEE P3329 Quantum Energy Initiative Working Group. Alexia, please go ahead and share work that collaborators are doing. And you have the floor. Thank you so much.
Thank you very much, Ed, for the introduction. and thanks a lot for the invitation to present this quantum energy initiative. I'm also very happy to have with me Pierre-Emmanuel Emeriau from Candela and Jeremy Stephen from Alice&Bob, because we are actively thinking about working together on these energetic footprints of quantum processors in their own startups. But that will be for later. So I will maybe complete a little bit the self-introduction to explain who I am and where I work. So as Ed told, I'm a CNRS Research Director, and CNRS is this big institution, governmental institution for fundamental research in France. And it is a beautiful organization that has labs all over the world. And I'm lucky enough now to have been affiliated to a lab that is based in Singapore with an antenna inside the Center for Quantum Technologies and antenna at NTU. So I actually pertain to a team which is then delocalized between France and Singapore, which is called the Quantum Energy Team. And with this, within this team, we study energetics of multiple quantum processes like quantum measurement, quantum optics, quantum transports, and obviously quantum technologies. For those who may search and may be interested by what I'm going to tell you now, there are open positions for PhD and postdocs. So please join me if you have some interest in the topic. So then I would like to start this presentation by a little bit of philosophy and take a high-level point of view of what we are going to discuss by discussing the concept of efficiency. So efficiency, it's something that characterizes all the machines that us human beings fabricate. When you don't want to execute a task, you build a machine and you ask this machine to do this task. And to do that, actually, the machine will consume material, energy, which are physical resources, and it will produce a result, a target result, with a quality of the performance that is quantified by a metric, M. And basically, we can define from there an efficiency, which is simply the performance divided by the resource cost of the resources that the machine has consumed. And basically, the purpose of science and technology is to increase efficiency. And this, we try to do it since thermodynamics started to define efficiencies. Okay, so the concept of efficiency, it's already well known in the case of classical computers. In the case of classical computers, the performance can be defined as the number of floating points operation per second, which are flops, and the resource is usually taken as the power consumption of the computer. And if you divide the performance by the resource consumption, you get a performance per watt with the unit of flops per watt. And since the first computers were fabricated, history has seen an increase in this performance per watt. And you see here the last years on this plot, the performance of the energetic performance of supercomputers. You see it increases, and actually it captures what is known as Kumi's law. Kumi's law is this increase in time of the performance of the processors, and this is a phenomenological law that acknowledges that this performance, it has doubled every 18 months since the creation of the computers. Unfortunately, for some reasons, it saturates since a decade. And so actually, oops, actually this, sorry, oops, I lost. Are you still hearing me? It seems
yes, we are still hearing you. No worry, Alexia.
Okay, thank you. Yeah, so what I was saying is that this Kumi's law, it has actually saturated, and this captures actually one of the problems that information and communication technologies are facing these days, which is the global electricity consumptions that they represent. 3 years ago, it was captured as 11% of the global electricity consumption. And again, there is no expected gain in efficiency because of the end of this Comey's law. There is also the problem of the raw material consumption. And this brings people to think that we need a paradigm shift in the way we process and information. And actually, quantum technologies could play that role. So what is the promise of quantum technologies? The idea is that we could boost the power of computing with quantum features. Here you have a very simple graph where you see the computing time as a function of something that we could call the problem size. You can think, for instance, about the size of a key that we are trying to break, okay? For this kind of complex problem, if you use a classical computer, the computing time exponentially grows with the size of the problem until reaching a point where actually the problem becomes untractable. The promise of a quantum computer is that because of the specificity of the quantum logic, this exponential growth in the computing time could be brought back to polynomial times. And this actually allows to define regimes that are known as the quantum computational supremacy, where a quantum computer can do what no classical computer could compute in a reasonable time, and the quantum computational advantage, when a quantum computer computes just faster than a classical computer on a useful case. Okay? So this is the promise of quantum computing, but these promises, they are made in the case of noiseless quantum computing. The problem of a quantum computer is that it's a very fragile object where any kind of noise will actually destroy the power of the computation. And to correct the noise, we need to involve some error correction that increase the number of physical steps, and that may actually ruin the advantages I was telling you about before. So the problem of the community of quantum computers is resilience of quantum supremacy and quantum advantage, and also to define the use cases of these various computing regimes that can be distinguished, okay? So this is well known in the quantum computing community. And now where I would like to bring the problem, and that's actually the goal of the Quantum Energy Initiative, is to see if it is possible to transfer these advantages on an energetic perspective. So here, what we would study is no more the performance alone, it's the efficiency of the quantum computer that can be defined as the performance taken as the problem size divided by the energy cost. And with this idea, actually, we can play exactly the same kind of game. We can try to see if a classical computer will consume more energy than a quantum processor. And we can actually define the same kind of regime where we would have quantum energy supremacy when a quantum computer solves a problem that no classical computer could do with reasonable energy. And we could also see if there is a quantum energy advantage when a quantum computer solves a problem with less energy than the best in-class classical computers and algorithms, okay? So here I'm using the conditional because these are goals that up to now the community has not really addressed. And actually, if you have a look at the literature, it is absolutely not clear if real quantum computers that we are currently trying to build, they will consume much more or much less than a classical computer. And this brought me to write down a perspective that was published last year. Quantum technologies need a quantum energy initiative that prefigurated the launch of the initiative I'm going to tell you now. So why, how comes that the research line that we need is still to come? It is because actually we have to face an interdisciplinary challenge. if you want to define an efficiency for a quantum computer, the big difficulty is that this quantity, the efficiency, it's a quantity that requires to connect data from different I would say, communities. Like I was saying, the efficiency is a metric of performance divided by a resource cost. Usually for a quantum computer, the metric of performance, it's defined at the quantum level. It's defined at the level of the quantum processor. While the resource cost, it's something that is consumed by basically enabling technologies. These are macroscopic resource costs that will be consumed, for instance, by the cryostats, by the lasers, by the microwaves, by all the classical electronics that is here to control the quantum processors. And so to compute and to optimize efficiencies, we need people from all the different layers of the stack here that makes the quantum computation. And this requires to put in synergy people from computer science, fault-tolerant, error correction, algorithmics, and compilers, which represent, I would say, the highest part of the stack here. We need to connect these people to people who do quantum energetics and quantum control that talk to the quantum processor here. And we need to connect them to people who know how to manage enabling technologies like cryogenics, lasers, and microwave. So this synergy that we need to create, these different areas of knowledge that we need to connect, this is actually the purpose of the Quantum Energy Initiative, to connect them in a way that makes sense. So this Quantum Energy Initiative, actually, it started with the PRX Quantum, the perspective I shown you, that was published in June. Then in August, with these co-founders here, so Olivier Ezratty, Janice Pletstoyser, and Robert Whitney, we have launched a website and a manifesto. And then in January, actually, after having reached a very reasonable amount of partners and signatures, we have launched the official board of the QEI, and we have turned actually the manifesto into a mailing list for open science. In May, we have launched the working group at IEEE, which is probably the reason why we are having this webinar right now. And again, I thank the IEEE people for this invitation. In June, we were reaching more than 300 participants over about 50 countries. In July, we have launched a YouTube channel, and the first seminar already took place. And our next step will probably to launch a COST European network. And in November, there will be the first workshop of the QEI in Singapore. So if you have some interest for the initiative, please have a look at our website. You can register anytime and get the news of the community. And it is still also possible to register for the conference that will take place in Singapore. These are the first industrial partners of the QEI. As you can see, there are academic centers and industry partners and HPC providers, and also quantum ecosystems all over the world. And the key scientific questions that we want to address within this emerging community is there energetic quantum advantage versus classical computing as quantum processors scale up? This is the question I told you about before. And how different this energy advantage would be from the usual quantum computational advantage, where just a quantum computer computes faster than the classical equivalent. There are also more fundamental questions, like the minimal energy cost of quantum computing if we take into account the classical context around, or a technological question, how to avoid energetic dead ends on the road to large-scale quantum computing. And obviously here we start with computing, but these kind of questions, we can actually decline them on all kind of quantum technologies, basically communication, sensing, and for any kinds of qubits, any kind of hardware. Okay, and the goals and missions of the QEI, they are to create a worldwide community, and IEEE for this is an excellent platform to start creating a huge network that will involve people all over the world working on quantum technologies. We want to propose optimization methodologies, framework, and benchmarks. And again, IEEE is a perfect actor in that line of thought. And we need to create a transversal line of research to do collaborative projects. And this webinar is a perfect example of this, because again, we are working together with Candela and Alice&Bob to see how it is possible to optimize the energetic consumption of their hardware. And we have the ambition to cover all qubit types, programming paradigms, and all quantum technologies. A little bit of advertisement for the working group at IEEE, which is called, obviously, the Quantum Energy Initiative Working Group. So I have the honor of being the chair. My vice chair is Dash Liu from China Telecom Europe, and the secretary is Marco Felus Asiani, who, for the little story, is a former PhD student who did a great job in actually putting together the foundation of the field. And the program manager is Jonathan Goldberg. And the idea is really to define an energy efficiency for quantum computing and quantum simulation by comparing the performance of the computation to its energy consumption. So basically what I told you already. Performance can be defined either at the level of the processor or at the level of the end user. And the idea is to apply this definition to all qubit technologies, including classical and quantum control chain, to various quantum processors, both NISQ era and fault-tolerant, as well as to quantum simulators. Again, a bit of advertisement. You are most welcome to join us. We need experts and countries we are going to write together. Ed, actually, I realized that I speak slowly. How much time?
No, you still have time, don't worry. Please continue, you still have time.
Okay.
Don't worry.
Okay. So, actually, I'm hearing your microphone. Maybe you can switch up your mic. Thank you very much, Ed. So, yeah, after this context that I just drawn, maybe I can give you a little bit more meat and describe you the first methodology proposal that was set up in my team, actually, by this bunch of people here. So if you're interested in what I'm going to tell you about, this all appears in this preprint that was just accepted in PRX Quantum. Marco, again, is my former PhD student and now postdoc in Warsaw and vice secretary of this IEEE working group. This is a very nice collaboration with Singaporean colleagues and Grenoble colleagues, in particular Robert Mutney and Wei-Kun N. So in this methodology proposal, what we do is actually setting up what we have dubbed the metric noise resource methodology, which is nothing but a very simple idea. Like I said, an efficiency, it's a metric of performance divided by a resource cost. And the ingredient that I had not told you about so far is the noise. And actually, in a quantum computer, there is noise. And for a given metric of performance, the bigger the noise, the bigger the resource cost. And so this is all about this triplet, metric, noise, and resource, that we need to describe and model within a full stack description of quantum computer. And based on this modeling, what we do is typically target a given metric of performance and minimize the resource cost for a target performance. So this makes a very long story short, but basically this captures the essence of the methodology. And this also captures the fact that we need a full stack approach because, again, the metric of performance, it's defined at the quantum level of the quantum processor, and it's the result of the fight between noise and control at the quantum level. And this is compared to the resource cost that is defined at the classical macroscopic level by enabling technologies. So in this paper, we have applied this methodology to the specific case of an ideal superconducting quantum computer If you like, this is an idealization of the Sycamore quantum processor that gave rise to the first demonstration of quantum supremacy by Google 4 years ago. And to make a long story short, we picked an ideal representation of these qubits, neglecting lots of sources of decoherence, and we picked a very specific error correction code such that we were able to perform analytic studies. And the net result is like this. We have studied the possibility to reach a quantum energy advantage with this kind of idealized device. And the useful task that we pick is breaking RSA key for different size of key, actually. We have considered the size of key, different sizes. First one is 129, sorry. And we have computed the energy consumption for classical supercomputer. I mean, we have not computed. INRIA has computed. And so we have here our classical reference point. And we have used the models that we have set to estimate what would be the consumption of a quantum computer with top quality qubits and STIN code. And what you see is that there are three orders of magnitude difference between the two energy consumptions, which points towards a quantum energy advantage. And this is for the case where there is no quantum computational supremacy, but we have also picked the case if there is quantum computational supremacy, because breaking this size of key is purely undoable for a classical supercomputer. And for a quantum computer, we still find an energy scale that is, I mean, within reach, and which also points again the existence of a quantum energy advantage. Okay, and so one question that we typically can ask is, but isn't that enough to reach a computational advantage? Because if you lower the computing time, obviously you will lower the energy cost. So we can explore further what is the relation between the quantum energy advantage and the quantum computational advantage. So this is what we did in this paper as well. And what you can see here are two plots where we study the computing time as a function of the size of the key we try to break, and the energy efficiency, again, as a function of the size of the key. And we do that for different types of quantum processors that suffer from different types of decoherence. And here, this plot here corresponds to the computing time of the classical equivalent, okay? So starting from here, you see that the quantum computers, they compute faster. So this defines the quantum computational advantage, okay? While here, this corresponds to the energy efficiency, which gets lower and lower for classical computer, and also a little bit lower for quantum computers. So you see that starting from these points here, the quantum computers, they need less energy to have the same performance that the classical computer, which defines the quantum energy advantage. And what I want to draw your attention on here is that the point where the quantum computer computes faster is never the same as the point where the quantum computer consumes less, which means that the energy advantage corresponds to a regime which is not the same as the computational advantage. And what is especially interesting in this is that there could be regimes and there could be quantum processors where one may save energy before saving time, which opens a nice perspective, for instance, for NISQ quantum processors, where actually we haven't yet shown any computational advantage, but we could hope to have an energy advantage before, okay? So obviously, these are all very idealized situations, and this needs to be explored within a real cross-disciplinary research line where we put together all the relevant expertise, which is the QEI. And this brings me to the last slide, which is a little bit of advertisement. little bit of advertisement for the conference that will take place in November in Singapore, where we have like a nice crowd in the organizing committee. We are going to address an interdisciplinary range of topics from fundamental quantum devices, algorithmic resources, classical information thermodynamics, quantum hardware, and high-performance quantum computing, and high-performance computing, sorry. And we have excellent plenary speakers that have accepted to join and to provide their vision to give an initial momentum to this venture. So the deadline for registration is still in 2 months, so you are most welcome to register if you're interested. And with this, I thank you for your attention.
Thank you so much, Alicia, for your great overview on the proposed full stack, matrix noise resources methodologies, and all the proposed early implementations with the superconducting qubits. And also a quick but great introduction about what your study group, working group is doing in standards and also your QEI initiatives. We really look forward to hear more from you and your collaborators in the near future. And actually, as you may know, there are actually a few questions in the chat box, but I would prefer that I will let our 2 speakers to speak first, and then we will come back to answer all the questions. But thank you, Alicia, great work.
Thank you.
And then, thank you. And so for our next 2 speakers that I will introduce very soon, they will share with us their plan to access and optimize the energetics of their quantum processing units in the NIQS regime, that is the noisily intermediate scale quantum computing, and the FTQC regimes, which is the fault-tolerant quantum computing. So let me formally introduce Mr. Pierre-Emmanuel Emeriau to all of you. Pierre-Emmanuel is a quantum information scientist working at the French startup Condé. There, he focused his efforts on envisioning the appropriate architecture for fault-tolerant quantum computing, which relies on single photons emitted from quantum dots. His work covers NISQ-related activities and lays the foundations for the fault tolerance in photonic quantum computing. As a later part, he is interested in the idea of the global resources estimation needed for such FTQC architectures. Pierre-Emmanuel, so thank you very much, and you have the floor to share with our audience about the great work you're doing. Thank you.
Thanks a lot, Edward. And thanks for the IEEE for this invitation, and as well for Alexia for this great talk as an introduction. So I'm going to talk to you briefly about what we do at Candela. So Candela is a startup, and we are building a photonic quantum computer. So it started in 2017, and now we're about 80 collaborators. So of course, mostly researchers and engineers in various fields such as optical technologies and semiconductors for the hardware parts, as well as algorithms, computer science, and theoretical physics for the theory. We do have a lot of academic partnership, of course. And last but not the least, we have a quantum processor available on the cloud since last November. So you can connect and go and try this quantum processor free. So this is what the hardware looks like for now. So Acela is the online platform we have. So it all starts, let me take the pointer. It all starts here at the quantum dot level at the top in black. So basically it's an artificial atom where you can shine a laser and it will emit a photon on demand. So then you can excite this dot with laser pulses. And if you filter out the laser, you end up with single photons that you need to time demultiplex because they arrive at different time bits. And so when you do the time demultiplexing, then you end up with photons that arrive at the optical chip, so the universal interferometer, at the same time. And then you can use a classical computer to actually change the active components of the universal interferometer and have a reprogrammable computer. So that's a global idea of our photonic platform for now, for the NISQ era. And so talking about the NISQ era, of course, because it's on the cloud, you can already do some sort of NISQ application. So just briefly, one thing that we did is have a toy example of a variational quantum eigensolver solver, where you just take a classical computer that controls a quantum computer, and so you take the expectation values of your quantum computers, loop that back in the classical processor that computes the classical parameters, the angles of your optical processor, and you try to find the lowest energy, so the quantum state of your Hamiltonian, and you see that you can reach very precise energies for your Hamiltonian. We also did the same for some classification data, where you need to find the correct label for pre-trained data. And again, you can do the same. You can use a variational quantum eigensolver algorithm to find a good classifier. Another example is that we used the computer to produce certified random numbers, and so basically you use some sort of a Bell test to certify your random numbers. But because it's on chip, of course you don't have the non-locality constraint, so you need to basically compute the crosstalk that you may have between the two parties. And if you manage to control the crosstalk and modify your Bell test, then you're able to generate again certified random numbers. And so why it's important to have this kind of NISQ application right now is that, well, because you can already see that the resource is very important, because, well, we do have a limit of what we can do with the current hardware. And so basically we need to find ways as theoreticians to improve the resources, or basically to put more and more resource in the small computer we have. And so that's already a hint of what we could do to, have a better performances. So basically it's a matter of compilation techniques, etc., etc. So as I said, we have a computer on the cloud, so you can just go on the cloud and try the computer if you want. And now, briefly, I'm going to mention the second half, so large scale. So basically, for large scale, I hope you see the video we have. So basically, it's kind of, so it relies on the same, building blocks of what I showed earlier, but basically, you need some sort of another framework to go to large scale with photonics, and you need what's called measurement-based quantum computation, which is slightly different than the gate-based model that people usually think of, although it's completely equivalent. And so basically, you can use the fact that you can generate entangled state at source from light-matter interaction to basically gain some sort of advantage in terms of having a better building blocks for this measurement-based computation framework. And then if you do that, you're starting to have, an architecture that you can rely on, and on which you can, apply what Alexia described just before, and have some figures to know what's the energy consumption of your device. And so to finish, I show you, so on the left, you have some numbers that were used from, computed from a paper from Olivier Ezratty that give you some, a rough idea of the energy consumption of some platforms. I should say is for photons, so of course it depends on the size you have, but for photons, now we are selling a computer to OVH, so it's a cloud provider in France, and actually the energy consumption is 2.5 kilowatts. And what I wanted to say is that, of course, if you want to go at scale and compute some sort of energy efficiency, you need to also be able to as Alexia said, go through all the stack. And one very important part of it is, when you try to play around with this quantum error correction code, and you see that, like if you want to have better performances, you need good quantum codes. And for now, people have mostly focused on, like the surface code or some class of codes where, like people know it's not very efficient for FTQC. And just lately, so last week, we've started seeing some development of quantum codes that are more efficient and where you see that you have better performances. And so if you plug that to what Alexia describes, then of course you're gonna have better efficiency because like this kind of architecture are just better inbuilt. And with that, I will leave the floor to Jeremy.
Thank you so much. So thanks for your introduction of all the work you have done in your startup container. Thank you so much. And then now, in the interest of time, we will introduce Jeremy Stevens. Dr. Jeremy Stevens is a quantum engineer at the French startup Alice&Bob. There, he works on developing large-scale quantum processors based on superconducting cat qubits. He became an expert of superconducting qubits technologies during his PhD studies on the subjects of fermionism, qubits, and quantum energetics under the supervisions of Professor Benjamin Ewer. He and his co-worker experimental work on the energetics of single qubit gates provide great insights into the energy exchange at play during the quantum operations. In relation to his current position, he is interested in the eventual energy consumption of a cat qubit-based fault-tolerant superconducting quantum computing. Jerry, you have the floor, and please share with our audience the work you have done in Alice&Bob. Thank you.
Thanks a lot for the introduction, Edward.
Good.
And thanks, Pierre and Alexia, for your presentations, which have given me a good platform to continue on. So yeah, I'm a quantum engineer at Alice&Bob, and I'm going to be talking to you today about our research efforts into the energetics of quantum computing. So Alice&Bob is a startup, which was a French startup, which was founded in 2020. And we've been undergoing quasi-exponential growth since then, and we've reached 75 employees as of today. And the premise of the founding of Alice&Bob was really that the belief that noisy intermediate scale quantum is probably not going to be enough to really get the most of the value out of quantum computing, and that we need to aim for fault tolerance in the end. And the reason for this is that noisy intermediate scale quantum computers are just too noisy to be valuable. And so as an example, Google's state-of-the-art Sycamore processor makes about 1 error every 1,000-bit operations. And to give you an idea of how bad this is 22 orders of magnitude higher error rate than in what we do in classical RAM these days. And so this basically is a very fundamental explanation for why the market size, which can be targeted by NISQ processors, is fairly small. It's like two orders of magnitude smaller than what we'd expect for FTQC computing. And so to reach fault-tolerant quantum computation, we have to both increase the number of qubits and improve their quality at the same time. And this will allow us to reduce the overall error rate by using quantum error correction. And so at Alice&Bob, what we believe is that if we increase the qubit quality far enough, then we'll probably have some kind of gain on the qubit quantity, so that we'll need less qubits in the end to do the error correction. And to explain how this is going to work, you need to understand a little bit about how quantum error correction works. And so in the classical world, if you want to correct for errors, you can just redundantly encode information, for example, here in 5 bits, and then use a majority vote to find out which single qubit had an error, correct for it, and essentially these 5 qubits these 5 bits, sorry, give you a protected logical bit. But in quantum computing, there are 2 types of errors, bit flips and phase flips. And so to correct for these, you actually need to use a 2-dimensional grid. In the case of the Bacon-Shaw code, this is a concatenation of a repetition code which corrects for phase flips and a repetition code which corrects for bit flips. And so you see that quantum error correction comes with a huge hardware overhead. In a sense, it's 2-dimensional with respect, it's 2-dimensional. But there's a way we think that we can reduce this, and it's by using CAD qubits. And so what these are is that we're going to take a harmonic oscillator and we use it as a memory, and then we engineer a 2-photon drive and dissipation mechanism, which is going to stabilize two opposite signed coherent states inside the cavity. And these coherent states are basically the most classical of quantum states. And so their superposition are what we call Schrödinger CAD states. And this approach has some nice properties. So if you increase the number of photons in the cavity, then you have an exponential increase in the time between bit flips, between bit flip errors. And so up to tens of seconds, essentially. And you pay for this only a linear decrease in the time between phase flip errors of the order of a few hundred nanoseconds. So you can get macroscopically long bit flip times and still measure coherence in CAD qubits. And so at these really high photon numbers, well, at high photon numbers, there's a regime in which bit flips are no longer an issue, and you can just use a 1-dimensional repetition code and correct only for phase flips for your logical qubit. And so this is what we call our hardware efficient approach. And we think it's going to reduce the hardware overhead needed for quantum error correction. So how are we implementing these CAD qubits? Well, we're using superconducting circuits. And so as an example, I've shown you a picture of our 4 CAD qubit processor, which we're currently investigating. And so this is the same type of technology that big players like Google or IBM are using. And so we're also using the same type of enabling technologies like the microwave control racks and dilution refrigerators. And so to bring this all to the energy aspect of quantum computing, essentially, I'm reusing the slide that Pierre-Emmanuel showed earlier. We're also inheriting the high energy footprint of superconducting circuits in this approach. So as you can see here in this table, which compares the different quantum computing approaches, essentially superconducting circuits have the highest power footprint of tens of kilowatts. And so this is like a strong motivation at Alice&Bob to ask the question, how can we reduce the energetic footprint of quantum computing and superconducting circuits in particular? And does our hardware efficient approach, does that translate into an energy advantage for quantum error correction? And finally, and putting in perspective what we're trying to do in the standards part of the IEEE, how do we write standards which are going to be effective at quantifying novel approaches, the energetic footprint of novel approaches to quantum computing, like CAD qubits? And so we really believe that at tackling these questions now at the beginning, at the emergence of this technology, is a important step in securing our long-term strategy. So with these few slides, I've given you just a bit of an overview of our approach, and I'm happy to answer any questions you might have about how we're doing this in practice during the question and answer session.
Okay, great. Thank you so much, Jerry, for the presentation about the work you have done in Alex&Bob. You can hear me, right? Because I'm using the microphone. Okay, great. Yep. And thank you all of you. Thank you, Alexia, and also thank you, Jeremy, and thank you also Pierre-Emmanuel for joining us today and sharing with us what is going on in the world of quantum computing. That is super exciting. And actually, I also see that there are quite a lot of questions that our audience may really want all of you or some of you to answer. So let me try to, choose some questions so that, and please let me know rather you want to answer a lot. The first one, I believe, it is the presentation from Alexia. The audience asked, does the quantum computer consume more energy than the classical computer? So Alexia, it can be a PhD thesis question, but do you believe that you can answer more later in a high level reply or anything that you can provide some quick insight to the audience?
So which question in the chat are you? The question two. Okay, does quantum computer yeah, well, that's the whole point of the Quantum Energy Initiative, to try to provide, first of all, a proper methodology to address this question. Because if you think about it, what should you count as an energy cost if you look at a quantum computer? Up to which level should you go? Should you take into account the energy that you're going to use during the computation only, or just before the computation? How much of all the material that is around the quantum processor should you take into account to list the energy cost? So this is something that has to be established properly, and this is actually the purpose of the working group, to be very systematic in the way we approach this list. And then that's a question of optimization, because, for instance, in the paper that I briefly advertised, we very clearly see that depending if we try to optimize or not the energy cost, we need nuclear plants or not. And so this is actually the goal of the community and of the initiative, to put together the proper experts to address this question and orientate the research and development to design the processors in a way that is energetically efficient from day one.
Okay, great.
I didn't answer the question.
Yeah, but the authors, the audience can always contact you offline for more questions, Alexia.
Sure.
But Alexia, actually, there's another question more about your presentation, your simulation result, because you can see from question 8, the audience asked, are the results theoretical, because the audience believes there's no error bar in the figure. Okay, great.
These are theoretical results, and so I don't know why this slide that is projected, because this slide is I think.
Tell me which slide you want to project. Oh, okay.
Yeah.
It's great.
Yeah, I'm autonomous. It's crazy. So I think this is this paper that the question is about, and indeed this is theory. This is theory using idealized figures, and the whole point is to now involve experimentalists to really measure the power consumption, the energy consumption, etc., which is very good, because Pierre-Emmanuel, is not an experimentalist, but Jeremy is, and they both contribute to fabricate real quantum processors. So I'm pretty sure there will be experiments measuring all the resource costs in their hardware, and yeah, we need more experiments in the field. Absolutely.
Thank you. But Jerry and also Pierre-Emmanuel, do you want to also elaborate on this question, or shall we go to another question?
Happy to elaborate maybe just on the first question that was asked about does a quantum computer consume more energy than a classical computer? So Alexia gave a very, I would say, a sort of long-term vision example And if I can maybe give an example, a today answer to that question. And so currently, with a 4-cat qubit processor, you can't do any of the things you can do with a classical computer. Essentially, you can do some things which you can't do with a classical processor because you have some kind of you can use entanglement and the superposition that is available in quantum physics, but you definitely can't do the same thing as a classical computer in terms of the magnitude of the complexity of the operations. And yet, like the final slide of the presentation was showing, current the numbers. So how do if I can get the slide, can you push to audience? There we go. Here, these 25, the bottom of the power consumption bracket given for superconducting circuits is very representative of the power consumption of the overall power consumption of our actual processor. And there aren't that many household computers which use 25 kilowatts for the level of complexity that we're currently running at. So there's a clear the point is that there's a moment in time in which these two paths have to cross, and we're not there yet.
Okay, great. Pierre-Emmanuel, do you want to elaborate also, or we shall go to another question?
I can elaborate a bit. Well, no, maybe we can go to another question because I see the list is quite long. So I guess.
Oh yes, actually, be honest, we may not be able to answer all the questions, but the next question, maybe let me choose this one. Question 17. Question 17 is saying that how to maintain the stability of quantum computing with high qubits during solving some important cases. Any one of you would like to answer this question? Question 17.
Yeah, I can take this one.
Yeah, great.
So basically, it's the point that I think we all mentioned is that you need to use quantum error correction. So I guess this is the point with high qubits. So I'm not sure what is meant by high qubits. Yeah. Well, I'm not sure what is meant by high qubits, but
high qubits, I don't understand either.
Yeah. But I guess to maintain the stability of what I guess what is meant to me is how the noise is not destroying everything if you're solving a problem for quite some long time. And so then you need to use error correction, as we mentioned. And so, of course, when you use error correction, you need to use like a lot of physical qubits to encode the information of one logical qubit. And so basically you have a cost, a resource cost associated to that. So you need to pay like some sort of trade-off. And so if you want to be able to come up with a solution that is not too costly, so costly in terms of implementable resource from a hardware perspective, and also, of course, in terms of energy efficiency, then you need to find very good codes that have a good rate in terms of physical qubits per logical qubits. And so that's like current research, like people are actively working in this area and like try to answer this question. Like we see a lot of papers going on the archive every day.
Okay, great. Maybe let me, I know this already 10 a.m. already, maybe we'll answer, answer the last question of the day. Question 12, where do you see the future of photonic computer architecture in quantum computing? Do you think that they have any relationship or correlation? So next year, Jeremy and also Pierre-Emmanuel, do you want to answer this question? I mean, the relationship and the future of the photonic computer architecture and quantum computing.
Yeah, so I guess maybe this question was asked during or when I was speaking, so I can maybe take this one. I'm not sure to understand the question because, so basically, and I guess this slide is perfect. Like you have what we want to build at the end is a quantum computer, and you have several technologies that may do so. Photonic is one of them. So basically, like a photonic quantum computer would be like an instance of a quantum computer. So they have a relationship in the sense that it's one example, but you have other technologies. So the technology of Alice&Bob with superconducting cat qubits, and also IBM and Google with superconducting qubits, cold atoms, trapped ions. So you have other technologies. And what's beautiful is that all technologies have advantages and drawbacks, and we don't know yet which one is going to be the leading technologies in the coming years.
Okay, great. So thank you all. Really, because we are over time already. So, but once again, I would like to thank Alicia, Jeremy, and also Pierre-Emmanuel for joining us today and sharing what is going on in the world of quantum computing. Just a very quick programming notes. Our Computer Society will host 3 different webinars in the near future. On September 7th, join us for a special presentation about conversation skill for engineers. In this webinar, you may learn the secrets to having effective conversations with team leaders, college and leaders. And also on September 14th, if you would like to know more about how to unlock the potential of an exceptional engineer, please join us for a webinar on that day, and our speakers will share with you some tips about how to make an exceptional engineer distinct from the good. And on September 27th, we will have another monthly standards webinar, and this webinar is about ECHO 2.1 data center network standard, which is the focus will be how to enable data center fabric convergence onto Ethernet. Once again, as I mentioned at the very beginning, we will share with you the presentation slide deck tentatively tomorrow, and you can also, because there are some links inside the presentation slide deck that you can have the contact information of some of the presenters today. And once again, I would like to thank all of our speakers and our society staff for joining us today, and all of you for attending for this lively Q&A discussion. Thank you again, and have a great rest of your day. Thank you, and bye-bye.
Bye, thanks.
Thanks a lot. Bye-bye.